All right, here we go. We are working on percent comp, yield, and limiting reactants today. Start off with a percent comp. What is the percent composition of magnesium and magnesium hydroxide? Okay, so we're going to need to know the magnesium portion of the molar mass. And here's the steps if you ever need to explain or so that you can check off as we go through them to make sure you're not missing a step. Okay, so find the molar mass of the substance. Okay, so when I'm looking at what's the molar mass of magnesium hydroxide, number one thing people do is they go, okay, that's the formula for magnesium hydroxide. What did that person forget? Magnesium has a +2 charge, hydroxide has a +1 charge. They aren't balanced right now. I would need a second hydroxide to make these guys balance. So I better do my crisscrossing. What's the rule when I'm crisscrossing with a poly? Polys need parentheses so that 2 from the magnesium goes all the way outside the hydroxide. That's how I get 2 hydroxides for every 1 magnesium. Now, if you're looking at the going, oh, I'm going to have trouble figuring out the molar mass from that because those parentheses are there. Okay, this is the appropriate chemical formula. Actually, you would show this without the charges for be the absolute appropriate chemical formula. But when you are working with molar masses, if these parentheses are bugging you, then do the same thing you do in math. Let's distribute. Okay, so when I rewrite this, magnesium stays that 1 atom that it was before, but I have 2 hydroxides. So 1 hydroxide has 1 oxygen, so 2 hydroxides has 2 times 1 or 2 oxygens. Same thing with the hydrogen. I can distribute that too. 2 times 1 is 2 hydrogens. So that makes it maybe a little bit easier to find the molar mass. So my molar mass, let's rearrange this into the molar mass equation. I have 1 magnesium and I have 2 oxygens and I have 2 hydrogens. I'm going to put those parentheses there so that oxygen does not look like a 0. 1 magnesium plus 2 oxygens plus 2 hydrogens will give me the molar mass of magnesium hydroxide. Now, instead of writing those elements here, since I need the molar mass or the mass in 1 mole, I need to put in the masses for magnesium, 24.30. The mass for oxygen, 16.00. The mass for hydrogen, 1.01. So 1 times 24.30 plus 2 times 16.00 plus 1 or 2 times 1.01. Well, I'm going to repeat that because I'm having trouble talking today. 1 times 24.30 plus 2 times 16.00 plus 2 times 1.01 gives me 58.32 grams per mole, or the molar mass of magnesium hydroxide. Okay. So the mass ratio, or my decimal composition, is the sum of the mass of the element divided by the molar mass. The mass of the element, that would be this whole first section here. Now, in this case, I'm taking 1 times 24.30. So that's not going to actually look that much different than just 24.30. But if you had any number there, you would still need to include that in the numerator. And the denominator is just the molar mass, 58.32. So this is going to give me my mass ratio, or my decimal composition. 24.3 divided by 58.32 gives me 0.4167. Okay, but that's not what it asks for. It asks for the percent composition. So to get the percent composition, we're going to multiply by 100. Okay, now it says multiply by 100%. Percent just means per 100, or 100 over 100, which is 1. Okay, this is why we're able to do it. It's basically a dimensional analysis, letting us change our units to percent. Okay, but when you plug it in the calculator, make sure you're just doing 0.4167 times 100. Don't put that other percent there, or it's going to throw off your answer. 41.67 would be my percent composition. When you take the SOL, it might say, what is the percent composition, and give you 0.4167 and 41.67. 41.67 is the percent composition, even if they do not show the percent sign afterwards. So either way they show it, 41.67 or 41.67%. That would be your correct answer because they wanted the percent composition. And as always, you can always plug this into your calculator and make sure, double check that you're using your calculator correctly, or even pause and do the whole problem by yourself and check your answers. What's our next one? Carbon dioxide. Okay, that is a prefix. So this guy we're going is covalent, CO2. Dioxides, 2 oxygens, is one of the 2 products of a complete hydrocarbon combustion reaction. If 4.5 times 10 to the 28 molecules of carbon dioxide are collected with 100% yield, how much mass is that? Okay, so this seems like a really hard, complicated, thick question, but we got a couple clues here. 100% yield, so I don't have to deal with yield at all. I just probably have some sort of dimensional analysis. Okay, I am starting with molecules of carbon dioxide, and they want to know how much mass is that. So when I look at my known and my unknown, 4.5 times 10 to the 28 molecules of carbon dioxide, and then how much mass? What units does mass have? Grams. How much mass is that? How much mass is that carbon dioxide? So this is not a stoic problem. They gave us all this extraneous information up top here that I don't actually need this time. Because why? They didn't give me a hydrocarbon. There's no CXHY here, so I can't do a balanced chemical reaction. So they just put that in there to throw me off. I want to just find how many molecules can be converted to grams. Okay, so that is my pathway, molecules to grams. This is not stoic, not stoic. Why? Because I have the same species. So what's the rule for when I'm converting? You don't see moles at the beginning and you don't see moles at the end. Magic moles goes in the middle when we have those same species. All right, so how do we start this off? Always 4.5 times 10 to the 28 molecules of carbon dioxide over 1. That's our start. And then we deal with our first arrow. Our first arrow is going from molecules to moles. So the from goes on the bottom, the to goes on the top. Molecules and moles are not the same thing. So when we go from molecules to moles, we use Avogadro's number. 6.02 times 10 to the 23rd molecules equals 1 mole. That is our unit conversion. That is our first unit conversion. And then what happens next? Then we have to convert those moles to grams. So we're going from moles to grams. We always divide out the froms and multiply in the twos. That conversion, grams per moles, that sounds familiar. That's molar mass. So I'm going to put the molar mass of who? Of carbon dioxide there. Molar mass of carbon dioxide. That's 1 carbon and 2 oxygens. 1 times 12.01 plus 2 times 16.00 is 44.01 grams per mole. Now, when you look at it this way, sometimes it's confusing. How else can we write that? 1 mole of carbon dioxide is equal to 44.01 grams of carbon dioxide. I just split it up. Instead of doing a divisor, I put it as a conversion on either side. So now we know 44.01 goes with the grams and 1 goes with the moles. Now we can divide out our units, molecules to molecules, moles to moles. I'm left with grams. I wanted to have grams at the end. Phew, I put in my unit conversions the correct way around. And now I can plug in that equation. If you're using Desmos, you're going to plug it in pretty much 4.5 times 10 to the 28. Just use that AB button or use a caret to get into that exponent spot. If you're using a calculator, 4.5, and then use the double E button, 28, and that gives me my start. 4.5 times 10 to the 28 times 1 times 44.01. So I'm finding what the numerator is. And I get 1.98045 times 10 to the 30. Okay, notice there's an E over there. Don't just write 1.98 or your problem's going to be way off. And my denominator is, change that to a different color. 1 times 6.02 times 10 to the 23rd times 1. If you're not using the E button for the bottom, you have to use parentheses or it's going to give you the wrong answer because it's going to mess up your PEMDAS. So now I have the numerator and my denominator. So I am going to take my numerator divided by my denominator. Again, use parentheses here if you're not using the double E button or you're not using Desmos to making sure, always make sure it's all the way underneath the entire divisor line. If not, go back and use the parentheses to make sure it's completely underneath that divisor line. And what I get, I'm going to plug that in again. 3.289 seconds. 1.9805 e to 30 divided by 6.02 e to 23rd times 10 to the 6. Okay, so that's 7.8. All right, so now we have our answer with our calculator. I'm going to go back over here to sig figs and underline the first two significant items. So I'm either going to round up to 3.3 times 10 to the 6, or I'm going to round down to 3.2 times 10 to the 6. How do I know if I'm going up or down? I have that H right there. So my answer is going to be 3.3 times 10 to the 6. Okay, and that 10 to the 6 is telling me it's going to be a really large number because it's a positive exponent. So that means it's going to be a large number. And that makes sense because we started with a lot of molecules, more than a mole's worth of molecules. Okay. Combustion of propane. So propane here is listed 3C3H8. Okay, so that is a hydrocarbon. Our X is 3, our Y is 8. So we have a hydrocarbon there. So we know we're always going to need oxygen to burn, and our products are going to be carbon dioxide and water. So that picture right now makes sense with what we've learned. It's just in picture form. Okay, and what is the question they want? What is the ratio of propane to carbon dioxide? So we know that when we're looking at the ratio of things that we look at the coefficients. So I need the coefficient for propane and the coefficient for carbon dioxide. Propane doesn't have one. Remember, if it doesn't have one, it's a 1. Plus, you could look up at this picture. This picture is hard to show, but it's actually showing some single bonds between those carbons. Okay, but there's only one propane there. Okay, and then there is 3 very distinct linear carbon dioxide models. Okay, so that is really good. So our ratio is 1 to 3. If they asked for the ratio of carbon dioxide to propane, it would be 3 to 1. So just read what the problem says for doing those items. Okay, and that's the law of multiple proportions or the law of definite proportions, depending on who you talk to, proves that those sets of carbon dioxide are also equal to moles of carbon dioxide. And do note, we do see heat and light on this side. So heat and light exited the experiment. So it is exothermic. Here we go. We have a teacher reacts 50 grams of hydrochloric acid. So I'm just going to write this right up top here, 50.0 grams, because that's the hydrochloric acid, with 25 grams of magnesium hydroxide, 25 grams of magnesium hydroxide, according to the reaction above. And they were nice. It looks like, yep, it came balanced for us. Always check that. If 22.5 grams of magnesium chloride are recovered, what is the percent yield? So right now, I'm not going to think of 22.5 as something that's in my stoich. That is my actual yield. So my theoretical yield, what the math said, is either going to be 22.5 or larger, and most likely it'll be larger. We're not good in the lab at getting 100% yield back. Okay, so before I find the percent yield, because that equation is percent yield is actual yield over theoretical yield times 100%. I have the actual yield of 22.5. I want to find the percent yield, but I am missing the theoretical yield. And as I said, that is what the math or the stoich will tell us. That's what the theory tells us. So I just got to put that on the back burner right now. And first I have to figure out the stoich magnesium chloride. All right, so I need the stoich magnesium chloride. And what units am I going to need it in? Grams. Okay. So I have 50 grams of hydrochloric acid, 25 grams of magnesium hydroxide, and I'm going to get so many grams of magnesium chloride. So where is my known equals question mark unknown? I have 3 distinct numbers. Well, I already figured out that's the actual yield, so I'm not going to need that in my stoich. I have 2 knowns. I'm actually going to have 2 stoichs. I'm going to have to do 50.0 grams of hydrochloric and find out how many grams of magnesium chloride that is. And I'm going to have to do 25 grams of magnesium hydroxide and figure out how many grams of magnesium chloride that is. 2 knowns, 2 stoichs. The only way I can avoid that is if they had said, and we have excess magnesium hydroxide, then you don't have a number. So then you would only have 1 stoich. But if they give you a number, you got to do stoichs. So that is my known equals question mark unknown. I now have to go with my path. My path is my units that I'm going from to my units I'm going to. So in both cases, I'm going from grams to grams. So I got to go look on my pathway for my gram to gram problems. If I start over here at grams and end with grams, my pathway is divide by molar mass, multiply by mole ratio, and multiply by molar mass. So those are the hints that I can remember if I have this mole map memorized. So that is the way to handle setting up that equation. Okay, you will not get that on the SOL. Nope, you will have to have it memorized. So when we set up the equation here, again, whenever we're going grams to grams, it's divide by the molar mass of the known, multiply by the mole ratio, and multiply by the molar mass of the unknown. Probably after doing multiple problems, you can kind of stick that in the back of your brain, as that's always what we do for grams to grams. That's the path. So our setup of our equation, known over 1, divide by the molar mass of the known. That means a 1 goes on the other side. Mole ratio. The mole ratio code is unknown coefficients over known coefficients. And then lastly, I'm going to multiply by the molar mass of the unknown. So a 1 goes on the bottom. That is our setup for both instances. So both instances, known over 1, divide by the molar mass of the known, multiply by the unknown coefficient over the known coefficient. multiply by the molar mass of the unknown. Okay, so let's work through this and see what this means. What are our knowns? 50.0 grams of hydrochloric and 25 grams of magnesium hydroxide. Now I'm going to do these ones separately so that we can just work off of it individually. I need the molar mass of my known. My known is what was on the left. So for this first problem, we had 50 grams of hydrochloric equals how many grams of magnesium hydroxide? So my known is hydrochloric, so I need the molar mass of the known, 36.46 grams. Unknown coefficient, who's my unknown? My unknown is magnesium hydroxide because that's who we're trying to find our information for. Who's our magnesium?